All right, let's get right into it. If you work with data, you already know the ugly truth. Data is almost never clean. It's messy, it's fragmented. That's exactly why today's explainer is laser-focused on Pandas. It is, without a doubt, the ultimate Python toolkit for wrangling that chaos into sleek, performant workflows. So let's jump in and see how we can supercharge your analysis. Here's our game plan for today. We're going to meet the data frame, tame some messy data, master the group by, combine our datasets, satisfy the need for speed, and finally, scale the whole thing up to big data.
Now, check out this recent quote from Geeks for Geeks. Pandas 2.0, a game changer for data scientists? Honestly, it's really not an exaggeration. The recent shift to the Apache Arrow backend has completely revolutionized data handling here. We're talking blazing fast speeds, beautiful memory management, and a fundamental shift in what you can pull off on a single machine. So definitely keep that power in the back of your mind as we unpack this toolkit.
All right, Section 1. Meet the Pandas data frame.
So if you're building a house, you gotta know your bricks, right? Well, in Pandas, your core brick is the data frame. Basically, it's a two-dimensional data structure. Think of it like a highly caffeinated spreadsheet. Sure, Pandas has a one-dimensional series, which is just a single column, but the data frame is really where the magic happens. And here's the absolute kicker. Unlike standard NumPy arrays that force one single data type across the entire grid, a data frame lets you have a specific data type per column. Integers over here, dates over there, text strings in the middle, all living together in perfect harmony.
You can have distinct columns holding entirely different types of information. Imagine floating point numbers sitting right next to actual timestamp objects. This structural flexibility is literally what makes Pandas the undisputed king for real-world tabular data. But okay, here is the multi-million row question. Once you've loaded a massive dataset into this structure, how do you actually navigate it? How do you efficiently extract the exact insights you need without your entire workflow grinding to a halt? Well, you really have to shift your mindset away from standard Python lists. For production-level analysis, we lean heavily on optimized methods. You've got lock for selecting data by its actual label, and ilock for selecting by integer position. Need to filter instantly based on specific conditions? That's where Boolean indexing and the ISN method come in, letting you slice through millions of rows in a fraction of a second. Seriously, stop writing standard Python for loops to search your data. Use these built-in tools instead. Moving right along to Section 2, taming the messy data. Because let's face it, your data is rarely perfect. Sensors fail, users skip forms, databases just drop connections. Pandas represents this missing data in a few specific ways, depending on the type. You'll run into np.nan for floats, none for objects, or pd.nat for missing timestamps. There's even a newer experimental NA singleton trying to unify all of this. But here is the critical takeaway. You absolutely cannot use standard equals equals operations to find these gaps. A null value does not equal a null value. You have to use specialized Pandas methods to hunt them down.
And when you do find them, you basically have two choices. You can perform an amputation using drop-na to just completely eliminate any row or column compromised by nulls, or you can perform a graft using fill-na to plug those voids with actual data, maybe the column's mean, a fixed string, or even just the previous row's value. Honestly, mastering those two commands is very often the difference between a successful model and a script that crashes hard with a value error.
Okay, Section 3. Master the group by. Once your data is clean, you actually want to learn something from it, right? Group by is easily one of the most powerful, yet somehow frequently misunderstood tools in the whole library. It's all about the split, apply, combine pattern. To really get group by, you need this mental model. Think of an active assembly line. First, you take a massive table and physically split it into smaller tables based on a category, like US states. Second, you apply an operation to each of those little tables, like calculating average revenue. And finally, the assembly line glues all those individual averages back together into one clean summary table. Split, apply, combine. But watch out for this trap. If you just write your group by code and hit run, you are not going to see your data. You're just going to get this weird data frame group by object back. Why? Because group by is inherently lazy. It preps all the internal groupings, sure, but it delays doing any actual math until you explicitly tell it what to do. It just sits there, waiting for you to invoke an aggregation like .mean, a filter, or a transformation. Once you understand that lazy design, it is incredibly efficient. Which brings us to Section 4, combining and merging datasets. So, what happens when your data isn't sitting nicely in one single data frame?
Data is dynamic. It constantly needs to be physically reshaped. Sometimes columns need to be gathered into rows, which Pandas handles beautifully with the melt function. Other times, you have long data where you need to spread those rows out into distinct columns using pivot. Being able to structurally rotate your data like this is absolutely essential before you even think about joining it with anything else.
And once the shape is right, we connect the pieces. Pandas gives you full-blown relational algebra capabilities natively through pd.merge. You can do left joins to keep your primary data perfectly intact while pulling in matches, inner joins for strict intersections, or outer joins to just mash everything together without losing a single row. If you've written SQL, you already know exactly how to think about this, but Pandas lets you execute the whole shebang entirely in memory using Python. Speaking of running things in memory, let's talk about Section 5, the need for speed, the final boss of data analysis. Because let me tell you, absolutely nothing is more frustrating than a script taking 45 minutes to run. Top developers completely agree on this. Iterating through a Pandas data frame with standard Python for loops is a remarkably bad habit. It is just so painfully slow because of the overhead required to check index alignments and data types on every single row. The absolute best practice here? Vectorization.
See, Pandas uses a convention over configuration approach. The API is designed to gracefully handle a crazy variety of edge cases and mixed data types behind the scenes. Now, that overhead is exactly what makes Pandas so wonderfully easy to use. But if you force it to run that overhead row by row in a loop, it's going to crawl. You have got to embrace vectorization, push those mathematical operations down to the highly optimized underlying C and NumPy arrays. Apply the operation to the whole column at once and literally watch your runtime drop from minutes down to milliseconds.
All right, final section, scaling to big data. What happens when your dataset is just so massive it threatens to crash your machine's memory? This is exactly where Pandas 2.0 changes the game. By integrating that Apache Arrow backend, it has completely revolutionized large-scale tasks. We're talking hyper-efficient operations for modern file types like Parquet, multi-threading for parallel execution on group data, and unified nullable data types. Basically, you can now process larger-than-memory datasets much faster, directly in Pandas, without having to immediately spin up a complex distributed platform like Spark. And you can leverage this power right now with 3 super practical steps. Number 1, stop loading data you don't need. Just use the use calls parameter when reading your files to pull only the specific columns you actually want. Number 2, convert low cardinality text columns, like say a column of US states, into the categorical data type. It drastically compresses memory usage. And number 3, for truly massive files, use chunking. Process the data in manageable batches rather than trying to swallow the entire file whole. So, there we have it. We've gone from the basic data frame all the way up to Apache Arrow memory management. Pandas is continuously evolving, giving you unprecedented power over your data workflows. Between mastering vectorization, leveraging efficient data types, and utilizing dynamic merges, you have everything you need. So the only real question left is, what messy, chaotic dataset are you going to conquer next? Thanks so much for joining me in this explainer. Now get